Hi all, today we discuss chapter 8 parallel transport. In our last classes we have discussed the derivative of a vector field along a parameterized curve alpha. This is the vector field x, and we define the derivative of we have already defined the derivative of this x along alpha. Alpha is a parameterized curve. If x is a smooth, if each xi xi from I to r is smooth, the derivative of smooth vector field x along alpha is a vector field x dot. This is denoted by x dot along alpha defined by x dot of t is equal to this x dot, the derivative vector field assigns a vector at alpha of t. This alpha of t is an element of the surface or the domain of the function f. Then the derivative of this is dx1 by dt, dx2 by dt, etc., dxn plus 1 by dt. So this assigns a vector. This is an element of Rn plus 1 at the point alpha of t. This is again a point of Rn plus 1. So this x dot t measures the rate of change of the vector part. This is the vector part of this parameter, this vector field along alpha. Okay, so this is this dx1 by dt is defined using the parameterized curve alpha. For example, we consider a vector field as a velocity vector field. If alpha is a parameterized curve defined as cos t, comma sin t, and this alpha is a function from open interval 0 to pi to r2, then the velocity vector field of this defines a vector field on R2. So this x of t is defined as alpha dot t. So this assigns a vector at the point cos t sin t, a vector minus sin t cos t. Now you can easily verify that this x of t is x of t belongs to S alpha of t. So this x of t is a tangential vector field. Now you can define the derivative of this x of t, x dot t. That is x dot t. That is defined as the derivative of this one. That is alpha double dot t. Alpha double dot t is at the point cos t sin t. This vector field assigns the derivative of these components. That is dx1 by dt. That is minus cos t, and dx2 by dt. That is minus sin t. So this is the derivative of this tangential vector field. So this is a tangential vector field. Then this is the derivative of that. Now we consider this x dot t. You can easily verify that this is not tangential anyway, because if you consider this this vector field at the point t equal to 0, then what is x of t? X of t is equal to at the point cos 0 sin 0, that is the point 1 0, it assigns a vector. This x of t assigns a vector 0 comma 1, that is minus sin 0 and cos 0. Now what is x dot t? So this x dot t is defined in this formula, using this formula, that is at the point 1 0 we assign a vector. This x dot t is again minus 1 comma 0. Okay, so you can easily verify that at the point 1 0 this derivative vector field of the tangential vector field x of t assigns a vector like this. Okay, this is the vector assigned by this x dot t. Okay, this x of t assigns at this point a vector like this. So this is tangential. So this x of t is a tangential vector field. Then when you take the derivative of this x of t, the tangential vector field, that need not be tangential at this point. Okay, that means derivative of a tangential vector field need not be tangential. So when you take the derivative of the tangential vector field, it loses some properties. Okay, it loses the tangential property of that vector field. Now in order to overcome this problem, we will use another type of we will define another type of derivative. That is what we call covariant derivative. So the chapter 8 starts with the definition of the covariant derivative along of a vector field, a tangential vector field along a parameterized curve alpha. Now we can see what is the definition of covariant derivative. In order to define the covariant derivative, we start with a vector field x along a parameterized curve alpha, that is from I to s, in an n surface. S is tangent to s along alpha, that is if x of t belongs to s of alpha t. So that's when we define this x of t as the tangential vector field. The derivative of x dot of such a vector field is generally not a tangential vector field to S. Okay. Now we will define a new derivative, new differentiation. This process of differentiating is called the covariant differentiation. This is the definition of the covariant derivative. Covariant derivative of x is the vector field x prime. The derivative, the usual derivative of this derivative of vector field along a parameterized curve alpha is denoted by x dot, but x prime denotes the covariant derivative. Then covariant derivative is defined in this manner. This is the usual derivative along alpha minus this times n of alpha of t. Okay, so what is the geometrical meaning of this? You take the normal derivative, then subtract some quantity from that normal derivative. Okay, so the geometrical meaning of this is this is the definition. X prime of t is equal to x dot t minus x dot t dot n of alpha of t times n of alpha of t. So this is the definition of the covariant derivative. The geometric meaning is nothing but if you define the usual derivative along alpha, then we subtract this quantity from this x dot t. Okay, when you take this as x dot t, we know that this n of alpha of t and this x dash t, this is our x dot t. When you consider this x dot t, then x dot t can be decomposed into two components. This x dot t can be decomposed into something times n of alpha of t and plus a vector along the direction of n composite alpha of t perpendicular. Okay, you can write any vector as a linear combination of a normal vector and the perpendicular vectors or a member of the perpendicular of n of alpha of t. Okay, when you consider the x, this dot product x dot t dot n of alpha of t, you can get by taking dot product on the right side, you can get this term will be 0 because this vector is orthogonal to n of alpha of t. Then by taking the dot product of n of alpha of t with this quantity, that will be 0, and this n of alpha of t dot n of alpha of t will give 1. Then this will be this component. Okay, so this will give the coefficient of n of alpha of t when you write x dot t as a linear combination of n of alpha of t and a vector perpendicular to that. Okay, so when you evaluate this, you can get this coefficient. So this times x dot t dot n of alpha of t times n of alpha of t will give this whole term, and when you subtract that quantity from x dot of alpha of t, you can get this one. Okay, so when you remove the component of x dot t along n of alpha of t, you can get this covariant derivative. Okay, this is the idea. The other thing, the other term, this will give the difference. X dot t minus this quantity will be this one. This one is always tangential at alpha of t because this n of alpha of t perpendicular will give the tangential vector field because this n of alpha of t is along we consider n of alpha of t, that is along the del f of alpha of t. Okay, some uh, one-dimensional subspace spanned by, okay, one-dimensional subspace spanned by this. Okay, so that is n of alpha of t whole perpendicular is same as del f of alpha of t whole perpendicular. So this is nothing but s alpha of t. This is the tangential space at alpha of t. So therefore we can get this different, this minus this quantity x dot t minus this quantity will give the component of this x dot t along the tangential direction. Okay, along the tangential at alpha of t. So then we can say that this x prime of t is again tangential at alpha of t. So even if this x dot t is the derivative of x, derivative of a tangential vector field is not tangential to alpha of t, we can get the covariant derivative. So that is obtained by removing the component of this x dot t along the normal. You can get this x prime that is always along s alpha of t. So this is the geometrical meaning. So when you define this x prime, you can say that this is some kind of derivative. This is defined as taking the usual derivative along alpha and remove the normal component of that. Then that is again some kind of differentiation. So this derivative has all the properties of the usual derivative. Okay, that is what we have to verify next. Then this can be considered as a differentiation because of this idea. X prime satisfies all the properties of this x dot as well. Now we will verify the different properties of this x prime. These are the properties of the covariant derivative. X plus y prime, that is the covariant derivative of this vector field, that is x prime plus y prime. This is the covariant derivative of x, and this is the covariant derivative of y, the vector field y. Then this is f of x, fx prime, that is the covariant derivative of this vector field, that is f dash. This is the usual derivative of f, the scalar function, times this vector field x plus f times the covariant derivative of this vector field. So the important idea we need to remember is when you write f dash here, this doesn't mean that it is the covariant derivative. Covariant derivative defined only for the tangential vector field. So f is a scalar function, so there is no meaning of taking the covariant derivative. So this represents the usual derivative. Since this x is a tangential vector field, then x prime denotes the covariant derivative of that tangential vector field. Similarly, when you take x dot y, this is a scalar function, so this stands for the usual derivative of the scalar function. Okay, d by dt of something. So that can be expressed as the combination of the covariant derivative. So usual derivative of the scalar function can also be written as x prime, this is a covariant derivative, times y plus x dot y prime. This is the covariant derivative of y, and this is the covariant derivative of x. So this usual derivative x dot y is a scalar function. So usual derivative of that scalar function can be expressed as x prime in terms of the covariant derivative. So this is the idea of covariant derivative. So the last one is already explained here. This is x dot y prime is equal to x dot y plus x dot y dot. These are the usual derivatives. So this is the usual derivative of the scalar function. And using the usual derivative, you can write like this. Then you can replace this x dot by x dot in terms of the covariant derivative. Then you can easily verify that this term will be 0 because this y is tangential. Then n composition alpha, n is normal, y is tangential. Then by taking the dot product, the second term remains 0. So that leads to x prime dot y. Similarly, x dot, this is the second term, that is x dot n, that is normal vector field, and x is tangential, then that one will be 0, then the remaining will be x dot y prime. So the covariant derivative of x dot y and x dot the covariant derivative of y. Okay, so this is the formula we have expected. So we can say that this covariant derivative satisfies the conditions of usual derivatives as well. Intuitively, we can say that the covariant derivative x prime measures the rate of change of x along alpha as seen from the surface. Okay, that means we remove the normal component of that. So the covariant derivative gives the component of the x dot usual derivative lying on the tangential plane of that surface. Okay. Note that the parameterized curve alpha from I to S is geodesic in S if and only if its covariant acceleration, that means covariant acceleration is the covariant derivative of the velocity vector field, is 0 along alpha. You can easily prove this. Now in the next class we will discuss the two kinds of parallelism, Euclidean parallelism and Levi-Civita parallelism.